Hello everyone. So today we are going to discuss on high level synthesis. Right? So I mean, as you saw in the last lecture is that we talked about this VLSI design flow, and we just saw all the sub steps of VLSI design flow, how we can take an high level behavior and we can map that to in integrated circuits. Right? So that is what we have seen. So in today's class we just recap that whatever we have discussed in the last class, and then we just go through high level synthesis primarily with an example, just to try to understand how what is the objective of each sub steps in today's class, right. So, if as you seen the last class is VLSI design flow is consist of several sub steps like high level synthesis, logic synthesis, physical synthesis, then fabrication, packaging and testing, right. So, and you can think about the actual thing start from that English language system specification, then we generate that C code from that manually, primarily manually, that part is not automated, and then we do high level synthesis to generate a register transfer level designs from C code, and then we do logic synthesis to get generate gate level designs, and then physical synthesis to generate transistor level designs or the physical layout, and then we do the fabrication and packaging to get the integrated circuits, right. And what is the objective of these cycles is we try to design as abstract level as possible, right. So that we can design in quick time, and we rely on the tools, CAD tool, computer aided design tools or EDA tools, electronic design automation tools to generate the next detailed level, right. That is the overall objective, so that we can generate a big circuit in quick time. So, that is the overall objective of VLSI design flow. We try to design as abstract level as possible, as quickly as possible, and try to automate that steps, use synthesis tools to generate the next level of designs, right. So, that is the overall objective, and this particular concept is nicely captured in this Y diagram, which consists of three axes, right, the structural axes, behavioral axes and physical axes. And so, if you just think about it, if you just go from the center to as far, that is more abstract design, right. So, if you just think about this, so in the code level, in the structure we have only transistors, right, and in behavioral level we have the functions that represent the transistor functions, right, and in the physically we have the layout, transistor layout. So, if you go one level up, so we will have gate level designs, right. So, we have gate flip flops in the structure level, and the gate level circuits can be represented as a Boolean equations, right, and physically we have the cells, the standard cells of the cell libraries. And if you go one level up, in the structure level we have the registers, multiplexer, ALUs, and physically you have register transfer level designs or the RTL designs, and physically either we go for ASIC or FPGA, right. And if you go more abstract level, so in structure we have processor, memory bus, in behavioral level we have algorithm flowchart in C code like this, and physical we have this PCB or MCM. So, this is how the whole VLSI flow stands, and we try to start designing from the directly from the algorithmic level, and that is the overall objective. And what is the importance of this design automation steps? The first thing is this sorter design cycle. As I mentioned, if you start designing, suppose you take an example of say sorting algorithm, right, and you just try to implement a bubble sort. So, if you write that bubble sort in C, it will just hardly 4 or 5 lines of code, right. But if you now think about I want to design the bubble sort in RTL level, now you have to consider all these registers, multiplexers, adder, subtractor, comparator, clocks, reset, everything. So, the bubble sort algorithm in RTL may be 100 lines of code, right. And now, if you think about a bubble sort in gate level, it asks you to design a bubble sort using gate level designs. Now, you have all this AND gate, or you have to realize the adder using AND gate on gates, or you have to use directly flip flops, registers and all those things, right. Now, your design may be 400, 500 lines of code, right. And now, if you think about I ask you to design a bubble sort in transistor level, which is maybe 1000 lines or 2000 lines of code. So, that actually give you the idea, right. If you just write a bubble sort, if you hardly 5 minutes you can write a bubble sort algorithm, and you can use high level synthesis tool, logic synthesis tool, and this to generate a gate level design or RTL level designs, or say transistor level design directly from using these tools. So, that is basically give you the sorter design cycle. So, that is the one of the important aspect of this. So, the next is the design space exploration. Again, if I ask you to implement a bubble sort, there may be more options in the hardware, right. So, for example, if you try to execute the whole thing in 4 clock, you might need 2 adder, or if I want to execute the whole things in say 6 clock, you might need only 1 adder or 2 adder, right. So, then you are using less resource, or there is a trade off between time versus the resource, and there are a lot of possibilities, right. In some cases it is okay to design everything in say 4 clocks instead of 6 clocks, or in some time you need to execute everything in say in 4 clocks instead of 6 clocks. So, based on your design parameters, you have a lot of options, right. So, basically you should always explore this design space, the possibilities to get the best result out of it. So, that is also possible through design automation, because it is automated technique, you do not have to design everything from scratch, right. And also the next possibility is the fewer errors in the design, because you just think of have to write a gate level design consists of 4000 5000 line of code, and you have to handle all clocks, all resets, everything. So, there is a high chance that you make some mistakes somewhere. So, you have to be very careful, I mean of not making many mistake in the design. But if you just think about a bubble sort, it is hardly 4-5 lines of code. So, you can easily write that easily, and there is a chances of errors is minimum or less compared to if you just design that in RTL or in gate level. So, if you use design automation, the chances of errors is less, and also there is another important aspect is specification driven optimization in the higher abstraction level. So, what is that? So, it's basically it is if I ask you to RTL design, so writing 4 variations of say bubble sort is will time consuming, right. But if I ask you, so you design one bubble sort just to give minimum in it is the fastest RTL which compute the whole thing in minimum possible time, right. Or I ask you to design another bubble sort which use least number of or the least number of resources. So, we have your abstraction goal or the design optimization goal may be different, and based on your goal, the RTL or the gate level design that you are going to get will be different, right. So, again you can have a high level code, you can always try do these things using synthesis tool, right. So, because you have a high level, it take very less time to design an algorithm. So, again if you just use this automation tool, design automation tool, so the specification driven optimization is easier, right. So, that is another advantage. So, this is why we mean most all the India industry or the semiconductors rely on this all synthesis tools, I mean provided by all these CAD companies, right. So, that is the overall objective. So, in today what we are going to talk about is high level synthesis, the first step. So, from that C, C++ high level behavior, from C, C++ we are going to generate the RTL and how. So, what we are going to do today, instead of discussing all the sub steps, algorithm behind that, and what is the logic going on behind, and complexities of those algorithms, we are not going to detail of that thing, right. If you just ask, I mean as a layman, if I ask you to write and ask you how you can convert a bubble sort algorithm to a RTL design, how we can do that, what will be our steps, or what are the common way to do that things, right. What are the steps we should follow, that we are going to discuss today, and in next class we are going to discuss more on how we can automate those processes, what are the algorithm going behind that, right. So, that we are going to discuss in the tomorrow's class, but today we primarily discuss on how manually or what were the steps that we should follow to convert a C code to a RTL design, right. So, as I mentioned, high level synthesis is basically, I mean converting a high level behavior which might be written in C, C++ to an RTL design. So, that you can see in the left hand side this code has a while loop, and we have certain kind of operations in that, and we are doing in a loop, and then we produce some output x, y, u and something like this, right. So, this is something a behavior and is kind of C. In the right hand side, after high level synthesis, we will get a register transfer level design which consists of a data path and a controller. So, data path will execute these operations in the hardware, right. So, data path is there to execute these operations, and controller is there to control the execution operations in the data path. So, finally, we are going to generate this kind of circuit from this, and we are going to discuss now how we can do this step by step, right. So, a high level synthesis consists of several sub steps: pre-processing, scheduling, allocation, binding, and data path and controller design, right. So, we are going to discuss all those things now, right. So, what is pre-processing? So, in pre-processing what we does, we try to represent that C code in some intermediate form, CDFG, we calculate the data dependency inside that, we do some analysis, we apply certain compiler optimization on that, to generate some optimized version of the intermediate code through which we can do. And then what we do? So, that is what is shown in this diagram. So, we start from a high level C code, we do pre-processing, we get a control CDFG control and data flow graph, and then what we do? We do the scheduling. So, in scheduling is what is that? So, we have multiple operations there, right. So, we cannot execute everything in one clock. So, we have to assign time step to the operation, or we have to decide which operation we are going to execute in which time step. That is something scheduling, right. So, that is what we are going to do next, and then we try to map those variable to the registers in the hardware, and we try to map the adder function units, adder multiplier to the function units of this into the hardware. So, that is called allocation and binding. So, after allocation and binding, we will get to know what are the variable will map to which registers, which of the operator is going to map to which function units, right. And once we are done that, we try to generate the data path. The data path is what we have, as I mentioned, the data path consists of the function units, we have registers and the interconnection component like multiplexer, demultiplexer and the interconnection between them. So, we try to generate such kind of data path out of this information. So, which we are going to execute these operations, right. And then next, once we decide about this, we have to control the operations data flow in the controller in the data path, right, and that will be controlled by the controller. We will discuss more on those in subsequent in this class. And finally, we are going to generate this, which is consist of a data path and a controller, and this controller every signal generates some control signal to the data path to execute certain operations, and after the operation it generates some data path gives some status signal to the controller. Based on that, it decide the next state. Okay, so, this is the overall flow. So, we will discuss those sub steps with an example. So, what we are going to take is a second order differential equation solver, which is very common is very is widely used example for any CAD courses. We will take this example and we try to see how we can generate an equivalent hardware out of this behavior, right. If you look into this behavior, it has some 5 inputs x, dx, u, a and y. Y should be here, so y is also here, and we have output is y, okay. And there is a while loop. In the while loop, we are going to execute when we do certain operations until x less than y, and then finally, here we are going to generate output, right. So, this is the overall algorithm, and we are going to discuss here how we can generate a hardware that is going to execute this behavior, right. So, now we will, instead of going into detail of these steps that we just learned, what we are going to discuss, what is the immediate step that we should do, right. So, if you will look into this behavior, first thing will come to your mind is that there is a while loop, right, and there are big operations, right. We cannot execute all these things in a single clock. Then what will happen? So, if you want to execute the whole operations in a single clock, the problem will happen is that you have to execute these 3 multiplier in a same cycle, then these 2 subtraction, there are 5 operations in a chain. So, your design will not have a good speed, right? Your clock that you are going to achieve through this design will maybe hardly some kilohertz or something, right. And also that there is a loop around this. Again, then this loop I do not know how many times it will execute, right, depends on this x and y value. So, again I do not know how many times I have to do this whole thing. So, how do you decide that I have how many clock I have to do these things, right. So, this is all these things are not possible to do, decide from this behavior. So, what we have to do, first thing we have to extract the what are the inputs of this behavior. So, that we already know these are the, and you have to read. So, when you have a hardware, we need to know we have to read these values, right, through some port, hardware port. So, basically in hardware there is the input are coming through some port. So, that means we have to realize these inputs or read these inputs through some port. So, that is what is these operations, right, that we have to read, suppose, and the number of port in the hardware is limited. So, we have to decide how many port we are going to use for this design, and say for this 5 reads I have decided to use 3 ports, say. So, then I am actually reading dx through port 1, x through port 2, a through port 3, y through port 1 and say y through port 2. So, that is what I have decided, that I am going to read this 5 inputs through these 3 ports using this logic, right. Okay. And also next is, we, as I mentioned, these operations, big operations cannot be executed in one clock, then your clock speed will be very less. We have to break this operation in small operation. For example, I can execute this is a sub operation, this is a sub operation, then we will do this, right. So, similarly, this is a sub operation, then this is another operation, then we do the whole thing, right. Then we make a so this is already computed, and now I am going to do this subtraction operation, right. So, this is how I am going to split this big expression into small part, and that is called 3 address code, right. So, what I did, the same example is here. So, I break these operations, I mean the whole while loop operations are here, I break them into 3 address code. So, what I did this 3 into x I store into T 1, I do u into dx, this u into dx I store in T 1, I take this 3 into x I store in T 2, and then I do this 3 into y here and I store into T 3, right. So, this is what I am doing here, and then what I am doing. So, now this is T 1, this is T 1, this is T 2, I am now I have to do this multiplication. So, I am doing this here, right, this T 1 into T 2 T 5. So, that is effectively this. So, this is become this T 5 is this, and then this is basically T 3. I have to now multiply with the dx, that is what I am doing here, T 3 into dx. So, this is become T 6, right. So, this is what I am doing here. So, I am breaking this big expression into 3 address operations. So, similarly, if you just see, if I break this operation, I am going to get this 11 operations out of this while loop, right, and I have to also execute this x less than a. So, that is also there. So, this is what I have done to break these big operations into small 3 address code, so that I can execute these operations in some function unit in the hardware, and we can achieve greater clock speed, right. So, this is what is that called breaking these operations into big operations into smaller operations. Then we have to extract, as I mentioned, this is while loop and there is a basic block inside this. I mean we have to, I do not know how many times this loop will be executed, this body will be executed. So, I am going to represent the whole behavior in terms of basic blocks. Okay. So, I have one basic blocks here which will do this reading operations. I have one basic block here that will do this the loop body. So, basic block is what? There is no branching statement there, all are sequential operations, and I have also have a basic block here just to output the value of y, right. So, I have 3 basic block, and that is what I have shown here, that is the input basic block. I am doing all these reading operations. This is the basic block, I am doing this body, loop body, and this is that output port, this is B 2, right, and this is that while loop, and this is called control and data flow graph. So, we extract and control and data flow graph from this behavior, right, which consists of set of basic blocks and their control flow. So, this is what I have done. So, we have done 2 things, we break the big expression into 3 address code, we extract a control or data flow graph out of it, right, and what next. So, this is so far we have done in the pre-processing steps. Now, you have to understand that. So, as I mentioned here, this T 1 is done here and then this T 2, and this T 5 operation depends on T 1 and T 2, right. So, I cannot execute these operations unless and until this and this is over, right, unless and until these are executed I cannot do this. So, that means there is a dependency between this operation V 5 with V 1 and V 2, right. So, this can only be executed once this V 1 and V 2 is over, right. So, that is called data dependency. So, once we are done with this control flow graph extraction and this splitting the operation into 3 address code, we have to extract, we have to find out the data dependency, and that among the operations of the behavior, right. So, if we just try to find the data dependency for this block, let us try to do that. So, this is the same block I copied here, and if I just take this, right. So, this is the data dependency from u dx, these are the input variable, and this is that operation which is a multiplier. So, I do multiplication and the output variable is T 1 and the operation is V 1, right. So, this is the data dependency. So, if we try to represent this whole this text or the body of this basic block using a graph, right, where each input is some variables and the circular nodes are the operator, and we try to find out the dependency between this, right. So, that is what I just saw. Similarly, if I just do this for this T 2, so T 2 is 3 and x and multiplication is happening and the output is T 2 and the operation is V 2, right. So, this is I just do it for this, and then since this is depends on this. So, if I just do this this T 5, so T 5 is now dependent on this T 1 and T 2. So, T 2 is this, I just write here. So, now this since T 1 this operation V 5 depends on our T 1 and T 2, this will come next, right. So, this is how the data dependency is expressed, right. So, this way I can, if I just draw the for each operations, I can construct a graph like this. So, this is called data dependency graph. So, we have to extract this data dependency from this basic block behavior, and what is signifies? It signifies the data dependency among the operations. So, what it signifies? I cannot execute V 8 unless V 7 or V 6 both are executed. Similarly, I cannot execute V 5 unless V 1 and V 2 is executed, and similarly for other operation, right. So, I cannot do this unless this V 4 is executed. So, this is how it actually give you the idea how the data dependency works and which operation will execute first and then which operation next, right. So, this is what is preprocessing. In preprocessing, we do some more things which I will not cover here, is basically the compiler optimizations. So, once you write a code like this, there might be maybe unoptimized code, right. We might have to might have a better version of this code which we have not written. So, then we can apply some certain compiler optimization technique like say loop transformation, say constant propagation, dead code elimination, common sub expression elimination, those kind of operations on this behavior to generate some C code which is kind of a more optimized version of that. So, that I am not going to discuss today, because our intention today is just to see how from a C code a RTL can be generated. Those are kind of advanced topic which will be covered in a specific lecture. Okay. So far we have done that. So, we have extracted this data dependency graph. We can represent the whole behavior as a CDFG, each expression are converted into three address code. So, this part we have done, right. So, now what is the next step? So, this much we understand. So, now we have a intermediate representations which is a basically CDFG, where each operation is a 3 address operations, and we also have the data dependency informations. So, what is the next step? The next step is to decide where I am going, in which clock I am going to execute which operation, right. So, that is our next step. So, what is that? For example, as I mentioned here, so this whole loop body cannot be executed in a single clock because of lot of multiplications and other operations are there. We try to do it in multiple clocks, right. So, now that we have to decide, and here we remember we usually do this scheduling of this each basic block separately. So, we try to, when we are going to decide the number of time step for this B 1, I am not going to consider this I 1, or when I am going to decide the number of time step required for B 2, I am not going to consider B 1. So, these are kind of individual block which we can decide the run time or the number of time step required to execute independently, but there are certain advanced techniques are there, path based scheduler, which actually take both paths, but those are advanced technique. We are not going to discuss on those in this course detail. Okay. So, what we are going to consider, we go to consider each basic block and try to find out how many number of clock we require to execute the operation inside this particular basic block, right. So, that is what is the next step, because that is what we have to we need to know how many time step is required to execute certain set of operations in hardware, right. So, now for this, as I mentioned, there are some dependency. We cannot execute this unless this executed. So, based on that we can decide I am going to use 4 clock time step. So, this is time step 1, this is time step 2, this is time step 3 and this is time step 4 to execute these operations. Let us say I have decided that, and now we see whether this data dependency is violated by this. So, here you can see that when I am going to execute all the input, all these 4 operations, the inputs are available. So, I can execute them, there is no data dependency on the other operations. So, this can be done in clock, there is no data dependency violation, right. Now, if you just think about this set of operations, once I am going to execute this, this is available, this is also available. So, there is no problem here. Similarly, this depends on input. So, so I can do it here itself, and this also, this T 4 is available and V y is available. So, I can do this. So, there is no dependency violation. Similarly, for this and this. So, this is what, say I have decided that I use 4 cycles, 4 clocks, right, or 4 time step, right, 4 time step to execute this 11 operations. So, in this behavior, as I saw, there are 11 operations. I am going to use only 4 cycle to execute all 11 operations, right. So, this is what I have decided. So, this is what is called scheduling, assigning time step to the operations. So, I am assigning time step 1 to these operations, I am assigning time step to these operations, I am assigning time step 2 to these operations, and time step 4 to these two operations, right. So, this is what is called scheduling, and this is our immediate next step, because once we have a behavior, it is untimed, there is no time assigned this, there is no information ki how many clock cycle you require to execute that we have to decide first ki how many clock cycle I am going to use here to execute that particular set of operations. So, that is what is called scheduling, right. So, this is done. So, what is the next step? So, this is the schedule information, and now we have to think about of the hardware. So, we have done with that ki how many clock cycle is required or how many time step is required, that is already done, and now we have to decide how many register we are going to use, or say how many functional unit we are going to use in the hardware, right. So, the obvious immediate solution is that I can store each variable in each register, right, that is that we can do. Similarly, I can use a separate function unit for each operator. So, that is the worst possible case, right, but the number of operator is huge and they will not be reused, right. So, that is not the purpose of hardware, right. In hardware, you try to use each operator in try to reuse them as much as possible. So, our objective would be try to use minimum number of register to store all the variables of the behavior. Similarly, try to use minimum number of functional units to execute all the operations of the behavior, right. So, each substep has some optimization goal. For example, in preprocessing, we try to generate some data dependency graph where the length of the dependency graph is less, right. So, that is goal, and because for that we use several compiler optimization technique to reduce that. In scheduling, what is the objective? The objective is try to generate some try to schedule all the operations in minimum number of time step. The objective is try to reduce the number of time step as much as possible. We might have some other goals that we are going to discuss later, but primarily try to execute all the operations in as less as clock possible, right. And then we go to this register allocation binding and function allocation and binding, where you try to use minimum number of register to store all the variable of the behavior. We try to use minimum number of function unit to execute all the operations of the behavior, right. Now, the question is how we can do that manually, right. So, intuitively how we can do that. So, let us see this example. So, in this example we have seen this is we use 4 time step to execute this behavior, 4 time step, and now we try to, the objective is here try to share some register to store multiple variables. So, how many variables are here? We have all these input variables, and we have also this in temporary variable, because we have introduced so many temporary variables, this T 1, T 2, T 3 and this. So, we have total let us see. So, 15 variables are there. So, there are 15 variables in this behavior in this particular code, and then so what we have just to recap this. So, what we have done, we just do the scheduling for this basic block 1, right. Similarly, we can do the scheduling for other block also, right, this basic block I and B 2. But since they are kind of the same, so I am just going to discuss only basic block 1. So, other is just the same thing we can do in the other block as well, right. So, now we have 15 variables. Our objective to use minimum number of register to store these variables, and the question is how. Now, if we just look into this behavior, this schedule information, the T1 is generated here, right, at the end of time step 1, and is going to use here. After this, it is not going to use in S3 or S4, right. There is no use of T1 in S3 and S4. So, there is no need to store T1 in for the time step T3 and S4, right. So, we can actually use the register that is stored T1 to store something else, because T1 has only required in the for the time step 2, where it is going to use here, other time it is not required, right. So, that is the overall idea. If some variable is not used in some alternate time step, you can delete the value in the hardware, because if the register is not stored, that value is not available anywhere. So, if it is not required, it is not required to store as well, right. So, we can do that. So, that is the idea. So, we try to find out the lifetime of each variable, and that is represented in a graph called interval graph. So, as I mentioned, for T1, it is just defined at the end of S1 and it will be available from S2, right. So, the lifetime of T1 is only in S2, right. It is only used in time step 1. After that, it is never used. So, there is it is live, it is basically it is not live variable, right. So, it is I can replace the value with something else. Similarly, for T2 also the lifetime is S2. For T3 is also defined here. So, it is for S3, it is in time step S3, this is T3, and T4 is defined here. So, lifetime is here, and for T5, 5 is defined here. So, this is for S3, right. So, T3 5 is defined in S3, and for T7 and T6 they are defined at the end of time step 3. So, they are available only live here, right. So, they are available in T7, T6 and T7 here, and for other variables like this input variable, they are actually, since this is a loop and they are going to redefine, they are actually has to be live for whole time step, because they are defining somewhere and they are going to reuse, right. So, their lifetime is for the whole 4 time step, right. So, this way I find out the lifetime of variables, right. Now, what we can do if, so lifetime means where I have the use of that particular variable, and I have to store that data for that time at least. Other places I may or may not, but that is there, this must to store that value, right. So, we try to use registers such a way that if there are 2 variables which lifetime is non overlapping, I can store them in a single registers. For example, here T1 lifetime here, T3 lifetime is this, they are non overlapping, and T6, right. So, they are in lifetime here. So, they are this T1, T3 and T6, they have a non overlapping lifetime. I am going to club them into a single register, and that is not violate any problem, and they are not going to problem in the hardware, because they whenever their data is used, that time that data is stored in that particular register. So, that is what is called register sharing. So, I am going to share a single register to store these 3 variables. Similarly, I can do this for R2, R5, T2, T5 and T7 in a register R2. So, other than there is no other possibility, because all are overlapping. So, they need a dedicated register, all these variables need dedicated register. So, that is what I have done here. So, I need effectively 11 register here, right. So, I need 11 register here for 15 variables. So, I have some saving, 4 register I have shared. So, you can think of this as a small example, but if you have big examples, there are hundreds of thousands of variables, then maybe the register sharing may be much more. So, that is our next goal, that I try to map those registers, because finally, I have to execute everything in the hardware and there is no variable, there only I have the registers. So, you have to map those variables into these registers. Now, if you think about the array in actual design, those has to be mapped into memory, RAM or ROM in the design. So, that is also another way of doing this. So, you have to think of the size of the array, and then you have to decide which particular array is going to map into which RAM, or whether it is going to map RAM or not. That is also decided by the use pattern. If it is only read only array, then it can be mapped to ROM, right. If it is read and write both are happening, then it is going to map into RAM. So, that is also similar way, but as far as our example concerned, I have only registers, I have only variables. So, I can map them to registers of the hardware. So, this is also done. So, this is the step called register allocation and binding. So, the next step is similarly the functional unit allocation and binding, and here in hardware you have to remember that the unit that is going to do multiplier, that is dedicated for multiplication operations, right. Similarly, the operation that is going to do addition, that is dedicated for addition. Maybe addition and subtraction can be done by the same operator, but multiplier addition can be a separate function unit. So, here I mean register is a unique type of thing. So, all variables will map to register, but here multiplier is going to map to the function unit, which is multiplier function unit, and the addition is going to map into the function unit, which is type of adder, right. So, we have to do this mapping for each type of operator. So, what I have done here is an example for our running example, how to do it for multiplier, right. So, again the concept is little bit same the way we do the register allocation and binding. So, if two operations are running in the same time step, right, for example, these two multipliers. So, I am going to do only for multiplier, other operations are not there. So, these two are in the same clock. So, same multiplier cannot be used for them, right. I have to use different multiplier for these two multiplier, or I would say there are 3 multiplier here. So, these 3 cannot be done in using same multiplier. So, I need at least 3 multiplier to execute these 3. So, I am going to represent their span or the use span for each variable in a interval diagram, in interval graph, where I have this time step S1, S2, S3 and S4. I am going to write a bar in particular time step where this particular operations is executed. For example, V1 executed here. So, I put a M1 here, I mean this bar here for V1, V2 is also executed in time step 1. So, I put V2 for V2, and then I put this for V4 bar in S1. So, these are the things done in for time step 1. Time step 2, I have 2 multiplication operation V5 and V3, this is V3, this is V3 and this is V5, and in time step 3 I have one multiplication which is V6, right. So, this is V6, and in time step 4 there is no multiplication. So, this is the interval graph for the from the usage of the multiplier this, right. Now, again the same concept, if that usage is overlapping, I cannot use a single multiplier to do that do this particular operations in the same time. So, we need different multiplier, but if they are used in different time step, I can use the same multiplier, right. For example, here I can use the same multiplier to do this, this two, even I can do this, but for some reason I decided this I am going to do V1 and V5 in multiplier 1, right. So, this is so for multiplier 1 I am going to do this V1 and V5. Similarly, I am going to do this V2 and V3 in multiplier 2, and in multiplier 3 I am going to use this V4 and V6, right. As I mentioned, for this, since there are 3 multiplier in parallel, I need at least 3 multiplier, but this mapping can be different. I could have done V1 and V6 together, even in fact I can do V1, V3 and V6 also in the same multiplier, but I just decided one of them, right. So, these are all possibilities, but you can choose one of them. So, I have decided this. So, this is called function unit allocation binding for multiplier. Similarly, I can do the same thing for adder, and I have assumed that addition and subtraction is done by a single function unit called adder, and you can see there are 4 adders here. This is 1, this is 1, this is 1 subtractor, and these are all adder or subtractor type. So, there are 4, but they are all in different clock step, right, in time step. So, these are all in. So, this is V10, this is V9, this is V7 and this is V8. So, I have done this in different clock step. Since they are non-overlapping, I can use a single adder or subtractor to execute all these 4 operations. So, I need only one subtractor or adder to execute this all 4 addition or subtraction operation in the behavior in the hardware. So, at the end what I have received? So, I got 3 multiplier, 1 adder, and similarly for comparator I need 1, because I have one comparator operator and this single operation I need a comparator. So, I got 1 comparator. So, I need 3 multiplier, 1 adder, 3 multiplier, 1 adder and 1 comparator, total 5 to execute all these 11 operations, right. So, 11 operations are there and I have 5 functional units, right. So, that is what we got from this sharing information. So, this is what we have done so far. So, you understand the concept, right. So, we first decide the time step when I am going to do which operation. Based on that scheduling information or that assigning time step operation information, we decide how can share some register to store multiple variables, that is called register sharing allocation, and then we again decide how to do multiple operation using a same function unit, and that is what is called function unit allocation and binding. And after that what we receive is this. So, we have the register mapping information, I have the function unit information, and in S1 I have done this for this 4 operation, right. So, if you just see here, I have done this V1, V2, V4 and V10. In S2 I have done V5, V3 and V9. Similarly, in S3 I have done this 3 operation, in S4 this. So, I just do it for 2 time step, I can do for S3 and S4 as well, right. This is S3 and S4 as well. But so, I have 4 operations here, and in S3 I have 3 operation, S2 I have 3 operation, in S3 also I have 3 operation, in S4 I have 1 operation, right. So, and now I have this register mapping information, I have this function unit mapping information, and now I can actually represent this high level behavior using register transfer level behavior. What is that? So, for example, in time step 1 or S1, I have operation T1 equal to u dx, but u is nothing but hardware, u is nothing but R5, right. So, I can replace this u by R5. Similarly, T1 is nothing but in hardware is R1. So, I can replace this T1 by R1, right. Similarly, this multiplier is nothing but M1, because V1 is happening here. So, I can replace this multiplier by M1 multiplier 1, right. And this similarly D6 is nothing but R7. So, I replace this dx by R7. So, now these operations T1 equal to u star dx is nothing but in hardware some register transfer level operations between R5 and R7. So, I am reading register 5, I am reading register 7, and I am doing the multiplications, and that result is stored in register R1. So, this is what is an register transfer level design operations in the hardware. Similarly, I can do this V2, I can replace this variable with their corresponding register name, and this operator with the corresponding multiplier, I will get these operations. Similarly, for V4 I will get this, for V10 I am going to get this, for S2 also these operations I am going to get this, for S3 also I am going to similar kind of thing, and for S4 also time step 4 also I get operations like this. So, then you can understand the basic block. I have 11 operations, first I partition them into 4 time step, and then I find the register informations, register mapping informations, I found the function unit mapping informations, and then I can actually represent that high level behavior is using the register transfer level behavior. So, I have now I do not have any variable, I do not have any operator, I have only registers and the operations, right. So, this is called register transfer level behavior. So, now actually map those high level behavior, at least one basic block into is equivalent register transfer level behavior, right. So, this is clear, right. So, now what is the next step? The next step is very natural, is I have to generate the data path, because I just make here, these are the operations I am going to execute, right. These are the operations I am going to execute in the hardware, but I have to make the connections, right, because here I just make this assumption, but in hardware what is going to happen, this has to be make the connection, proper connection here, so that this operation can happen, right. So, if you just think about, I have this is say R5, this is say R7, and so this is the multiplier. So, I have to make this connection to this is R1, then only this will happen in the hardware, right. So, this is this kind of connections I have to make, and I have to make this connection because I am reusing this multiplier, this may not be a direct connection, I have to make add a mux here, right. So, because multiple input might come here, right, because I am sharing. Similarly, here also this might go to multiple places. So, that is called the data path generations, and the objective is to minimize this interconnection cost, use minimum number of multiplexer demultiplexers just to make the connections, right. So, that is the objective of this data path generation, and that is our next step, data path synthesis. So, what I am going to do here, I am going to do it for 1-2 operations in the data path connections, and then you will understand the how the things works, right. So, as we have decided, I have 11 registers. So, this is my final hardware is I am going to generate. So, I have 11 registers here, I have 11 registers here, I have 3 multipliers. So, I have multiplier 1, multiplier 2, multiplier 3, I have 1 adder, I have 1 comparator. So, this is what is the components that is already decided here. Now, I have to make the connection for these operations, right. So, let me do it for this operation first, right. So, I have a connection to multiplier from R 5. So, from R 5 to multiplier 1 I make this connection, right. So, this connection is made, and then this is the right RHS operand for this multiplier. So, from R 7 I make this connection, right, and the result is stored into R 1. So, this is going to R 1, you can see this is going to R 1. So, just to do these operations I make this connection. Similarly, if I just do it for R 2 for this V 2 operation V 2, I have to make the connection from R 10 to M 2, R 10 to M 2, and then R 6 to this multiplier 2, R 6 to multiplier 2, I make this connection, and the result is going to store in R 2. So, this is going to this into R 2, right. So, this is done. Similarly, I have to make the connection for this R 3. So, for V 5, so from R 5 to this, R 5 to this, R 7 to this, and the result is into R 3. You can understand it is going to R 3. Similarly, for this, right. So, R 6 for this adder, it is coming from R 6 and R 7, and the output is going to R 4. You can, so this is going to R 4, right. You understand this. So, for the time step 1, I make the connections, there is no problem, right. Now, if you just go into this time step 2, what will happen? Let us again going to consider this. So, now this is already done, and for that this is the connection I received, right. Now, if you just think about this operation. So, now the input of multiplier 1 is coming from R 1, right, but earlier it is coming from R 5. So, now I need a multiplexer just to decide between R 5 and R 1, right. So, this is what I have done here. So, in the previous diagram I have only direct connection from R 5 to this, but once I consider this connection, now I have two more options, R 5 or R 1. So, I have to use a multiplexer, and I need a control signal here just to decide between R 5 and R 1. So, 0 means R 5, 1 means this R 1, right. So, this is what I have to add this multiplexer. Similarly, for the right hand RHS this right operator, I have earlier R 7, now I have R 2. So, I need again a multiplexer that will choose between R 7 and R 2. Right. So, I need this multiplexer, and this contrast 0 means this R 7, 0 means this, 1 means this, right. And the result is going to R 2, but in earlier time step R 2 data is coming from M 2, now it is coming from M 1. So, I need a for at the input of R 2 I need a multiplexer that will choose between this R 2 sorry this M 1 and M 2, because in first context this R 2 input is coming from M 2 multiplier 2, now it is coming from multiplier 1. So, I need a multiplier here 1 that is choose the input from either from multiplier 1 or multiplier 2 at the input of R 2, clear. Similarly, if I just consider this one, I have to again the problem will come for M 2, I have to add this multiplexer here, but you can see here there is interesting thing that V 2 stored is R 10, right. Now, also it is coming from R 10. So, I do not need a multiplier, this in both the cycle this is data is coming directly, I do not have to use a multiplier here. So, that is kind of a saving, because if you just add a multiplexer is useless. In first clock is going to select R 10, second clock also is going to select R 10. So, effectively that multiplexer is redundant. So, I am not going to use it, right. But for the right hand side earlier it is taking from R 6, now taking from R 8. So, I have this is R 6 and this is R 8, I need a multiplexer here, and the control signal 0 means this R 6, 1 means R 8. And for multiplier 3 there is no multiplier 3 here, and for adder now it is coming from R 8 and R 3. So, I have to add multiplexer similarly, and the result is storing into R 8. So, there is a defined now. So, then this is no multiplexer is required, because it is updating a new register now. So, for these two time step I make the connection. So, if I just add for S 3 and S 4 this way, the final diagram will get this, right. So, I can see that the multiplexer at the input of this multiplier 1 have only 2 inputs, and this also need 2 inputs, this needs 2 inputs, but for the adder when there are 4 inputs possible input, and there are 2 bits control signal is required 0 0 0 1 1 0 1 1. 0 0 means it select this, 0 1 means it will select the second one, 1 0 means it will select the third one, and if it is 1 1 then it is going to select the fourth one, right, and so on. Similarly, here also I need a 2 bits control signal to select between this, and I have added multiplexer only for 2 register, other is multiplexer is not required because it is only one data is coming to this. So, this is the overall data path that is going to be generated from this informations, right, from this informations, from this register transfer operations, this is the data path is required, right. So, this is the final data path that is generated out of this information, right. So, data path is ready. I have 11 registers, 3 multiplier, 1 adder, 1 comparator. I have 1, 2, 3, 4, 5, 6, 7 multiplexers and the interconnections, right. So, this is the data path that is generated. So, we are almost at the end of this task, right. So, only left is control signal and controller generation. So, what is the need of controller and what is that we should understand, right. As I mentioned here, this multiplexers is not now it has to be controlled, right. The data flow from the input to the output of multiplexer has to be controlled by these control signals, and that has to be generated, and for different control step or the time step, the operation that are going to execute in this I mean the selection that is going to happen here is different, right. So, how many control signals are required here? I need control signal for FU, for this or all multiplier I do not need, but here I need one because it is going to do add or sub, right. So, 0 means add, 1 means sub, or other way. So, this is 1 means add and 0 means subtraction. So, I need a control signal to tell this adder this function unit to perform either addition or subtraction, right. So, that will be decided by this. So, I need 1 bit for the function unit, for all other I do not need, and then I need the control signal for FU marks in the multiplexer, that are the input of the FU's function units, right. How many bits are there? 1 bit for this, 1 bit for this, 1 bit for this, 2 bit for this, 2 bit for this. So, 2 to 4 and 3 7. So, I need 7 bits of control signal to control the data flow through these multiplexers, right. And then how many register? Okay, the next important thing is that if this register enable. So, this registers, unless you control the write to this, is going to write in every clock, and that will, so that the garbage data will be written. So, we have to control the writing on the registers, and we need the write enable signal, right. So, once the write enable signal is there, then only the register will be updated, otherwise it will hold the old value, and that is very important. Otherwise, what will happen? Even if you are not doing any operations, if you do not control the writing on the registers, what will happen? It will just store some, it will update with some garbage value, and you have no clue what is happening there, right. So, that is very important. So, we need register enable signal, write enable signal for our registers, and I have 11 registers. So, I need 11 bits for that, okay. And I have 2 marks here and 2 bits. So, I need 2 bits register marks in 2 bits, right. So, this is what the number of control signals required. So, total number of control signal is required is 1, 7, 8 plus 11 plus 2 is total 21 bits, right. 21 bits control signal is required, and that is order is this, right, and I use the color coding to decide that. And now we have to decide in time step 1 what will be the control signal, right, or the control assertion pattern for time step 1. So, as I am doing addition in the time step 1, right, I am doing addition, the function unit I decide 1, right, and the next 7 bits represent the marks input, right. As I told you that 0 means it will select this, 0 means select this. So, I am going to give 0 here to perform this operations this, and then I have to give 0 here to select this and to perform this operation, because I am now in time step I want to execute this operation, not this operation, right. So, based on that I am giving this 0, here also I have to give 0 0 and 0 0 to select the first one, right. So, that so the control signal to the multiplexer is all zeros. And then I am writing 4 register R1, R2, R3 and R4 in the time step 1. So, this write enable signal will be 0. So, these are the next signals are the write enables, right. So, this all the 11 bits are write enable, this is R1, this is R2, this is R3, this is R4. So, this is the write enable signal for these R registers, and all other registers will not be updated. So, they will be 0, right. And then I need here multi signal for this, right. So, now here I am updating register 1 from multiplexer 1. So, this is 0, and I am updating from multiplexer 2, sorry, multiplier 2. So, this is 1, right. So, this is 1, right, sorry. So, this is 0 1 for this. So, this is 0 because it is updating from multiplier 1, this is updating from multiplier 2. So, this is 0 and this is 1, right. So, this is the control signal. So, you understand this in the first clock controller will generate these signals to this data path controls, right. So, that it is effectively execute this only these 4 operations, nothing else, right. So, that is what is going to happen. Similarly, let us discuss that S2. So, again I am going to do addition. So, I need 1 here and the rest these 7 bits are for the multiplexers, and now I am going to choose the second input. So, I need 1 here, I need 1 here and I need 1 here, I need 0 1 here because I am going to select the second one, 0 1 here. So, the control pattern is this 1 1 1 for this 3 multiplexer and this 0 1 here, 0 in here. So, this is the control signal for the multiplexers. I am updating R1, R2 or R8. So, this is R1, this is R2 and this is R8, rest are 0. So, this is that write enable signal for the registers, and I am updating here R2 and R1. So, I need 1 and 0. So, this is the control assertion pattern that has to be generated for the control step 2. So, similarly, I can generate the control signal for S3 and S4, when you understand that, right. So, this is I am done now, right. So, what I am getting here. So, this is the final data path. So, the final RTL. So, I am done with everything. So, I have generated described the data path. This is my final data path, this is my final data path. I have the controller FSM, which is nothing but this. How I am going to get this? So, I have just talked about this 4 time step, and this is nothing but B1. So, I just replace the B1 here by these time steps, and similarly, I am going to schedule this I1, and for the example that I took, it need 2 clocks time steps. So, you need 2 steps. Similarly, for B2 I have only 1 operation. So, I am going to replace that by that particular time step, right. So, this is say S5 and this is I1 and I0. Okay. So, this is my controller FSM. And in what it does, in controller every time step it generates the control assertion pattern, right. So, I just talked about the control assertion pattern of S1 and S2. So, that for S1 this is the control signal I just talked about. So, for S1 also have some control assertion pattern, S3 also have some control assertion pattern, S4 also some control assertion pattern, here also some control assertion pattern, here also and here also. The assessment such that is going to execute only that read, that because in this block I am doing this reading from port, right. So, that will execute the read operations from ports. Here this is for the basic block B1, all the operations that we were discussed, right. So, finally, we got this whole RTL, right, which is consist of this and this. I mean, this is the part of only this. So, we have some certain other data path for this and certain data path for this. So, this is the overall structure, and what is the status? So, I am doing this comparator, this will go to directly fed into this controller. So, that I am going to decide whether I am to from this state I have to go this or this, right. So, this is decided by the status signal. So, this you understand, this is the final RTL that we generate, which is going to execute that differential equation solver, right, that I have shown in the earlier at the start of the presentation. So, that is the C code and this is the equivalent RTL, and what we have discussed here is basically how we can generate hardware out of this, what is the intuitive next step to generate an hardware out of it. I do not discuss any automation or the algorithm so far, I just show this is the logical way to generate an hardware or a register transfer level design out of a C code or a high level behavior, right. So, now I do not talk about other aspect, I will just briefly give you some idea. For example, I decide about this scheduling, right, and it has also 4 time step, but if I just think about another version where I just do, because these operations here depends on input, I could have done it here also, right. So, if I just do it, this is another schedule, right, you understand this, right. So, now this also depends on only input. So, I can put this to here. So, I just put it here T3. So, I can do this 5 operations in time step 1, that still I need 4 number of time step, but here I need 4 multiplier, at least 4 multiplier, right. I need 4 multiplier, here I need 3, we already discussed. So, this is better, right, because I need only 3 multiplier, the same time I am executing this in 4 time step, I need 3 multiplier, I need 4, I always take this, right. So, there is a difference. The possible, there are other possibilities are there, I choose this for some reason. Similarly, you can do one more things here. So, since this I need 4 time step, after that this part are idle, right, I can move this to this time step and this to this time step, then also this is fine, there is no problem, right. So, this is that schedule. So, the advantage here is that still I have 4 time step, I am executing the whole thing in 4 time step, but the advantage is now see I have 2 maximum parallel multiplier, there are 2 multiplier parallel, 2 multiplier here. So, I need maximum 2 multipliers, 3 multipliers instead of 3 multipliers. So, this is better instead of this. So, what I am trying to emphasize here is that during scheduling there are multiple options and you never know which one is better, I just saw 3 possibilities, one is generating 4 multiplier, one is generating 3 multiplier, one is generating 2 multiplier, but all are using 4 time step. So, that is what I call the design space exploration, and based on your objective or based on your target, you might choose this one or you might choose this one or you might choose the other one. So, that is something is the choice or the design space exploration or the design targets. So, scheduling technique is something is how to automate this whole thing and check which is the best one, right. So, that is what is called scheduling, and we are going to discuss all these techniques in the next class. So, there are different kind of scheduling, ASAP, ALFE or resource constraint, time constraint. So, we are going to discuss those algorithms and how we can automate that process in next class. So, that is what is there. So, initially what I just saw, I just give you some schedule without thinking how we have done that, but now we have to automate that process, right. And during automation I can add, it can be unconstrained, it can be resource constraint, it can be times constraint, and it can have various kind of algorithm. Some of them are basically exact solution, some of them are heuristic, these are all heuristic, this is exact. So, we have different options, right, and we are going to discuss various scheduling techniques in tomorrow's class. Okay. Similarly, if you just go into this register allocation and function unit allocation binding, we have various possibilities. I show you in that particular example here that instead of this mapping, I just show you here that instead of this mapping, I can have a different mapping also, right. I could have do this, this and this in one multiplier, right. So, I can do V1, V5 and V6 here also, right. So, we can have the other options, which one is better, I know, I do not know, right. So, maybe if you do this, the interconnection cost will less, I have to use less number of multiplexers, or if you have to do this, this may be the best option. So, there are multiple options even using the same number of multiplier. If I told you you can use 4 multiplier, still you can do that, you can use 6 multiplier and you can do all the operations differently, that is also you can do that, but which one going to have the less number of resource, and the interconnection also depend on this kind of mapping. Similarly, register transfer also there are this mapping also can be different. So, T1 instead of T1, T3, T6 I could have stored T1, T5 and T7, that also I could have done. Instead of this I can store T1, T5 and T7, that I could have done. So, there are other possibilities are there. My point here is just to emphasize that point that the choice is not unique, you can have multiple choice and you never know, and all are interdependent, that if you do one kind of scheduling, the kind of register sharing you are going to generate is different, or if you do kind of register sharing or function unit sharing, the kind of interconnection that you are going to generate will be different. So, we are going to talk about those techniques, and how these things are interrelated, this more detail in tomorrow's class. So, in tomorrow's class we are going to discuss more on this various scheduling techniques, how we can automate this FU allocation and binding techniques, steps, and how this data path is depend on all these steps, that we are going to discuss in the next class in more detail. Thank you.